I'm going to talk about some sort of basic concepts in InfoViz that might be helpful to you when you're designing visualizations or infographics or maybe charts, just choosing appropriate charts. And then I'll get into some maybe tricks and strategies and design guidelines and some things connected to research issues towards the end. So here's a really simple data set. I've got sales figures that are a function of different regions. So I guess everyone can see that, right? There's no reflections on the screen. What would be a good way to visualize this with a chart? What would be an appropriate chart for this data? Sorry?
I said Jerry, because Jerry just did a presentation on this.
Perhaps a bar chart?
Yes. So is this something that everyone has seen before, like basic charts? Have you seen visual channels, the hierarchy of visual channels, like position is better than length, better than angle, stuff like that? No? Okay. So anyways, a bar chart is the perfect chart for this type of data. We've got one variable, which is a function of another variable. And so we could think of this variable as being dependent on this independent variable, right? And it's a little bit awkward for me to say independent and dependent. It's easy to mishear what I've said. It's easy to make a mistake. So I'm going to use some different terms. I'll say measure whenever something is a function of something else and a dimension for an independent variable. So when we have one measure that's a function of a dimension, a bar chart is often a good choice. Another choice that's often used is a line chart. So that might be appropriate if the dimension is time. So here's another data set. Here we have two measures that are a function of a dimension. So I could use two bar charts for this, or maybe two line charts. Maybe I'm not so interested in the dimension, but I'm really interested in these two measures and how they're related to each other. So is there a chart that comes to mind that would be good at showing two measures? Stacked bar chart, maybe. So there's more than one possible approach. Another one that's pretty basic is the scatter plot. So you've got two axes and each of them shows some measure. And so this scatter plot is showing these two measures. It's not showing the dimension at all. In this case, we just have 5 points, so we could add little text labels to each of the points to show what year it is, but adding text labels doesn't really scale very well. But anyways, if you do have two measures, one thing that should come to mind is maybe a scatter plot. And here we have the opposite case. Here we have two dimensions, and we have some measure that's a function of those two. So in this case, one of the basic types of charts we might consider using is the heat map. Okay? So I've just shown you three examples of simple data sets with a small number of variables in each case. And I've explained these terms already. So what if we have lots of variables? What types of approaches are there? So one is to use a face. This is an idea from the 70s. And so maybe the intuition here is that babies seem to be able to recognize faces. There's probably stuff in our nervous system and in our brain which is adapted to recognizing faces. Maybe there's some way we could leverage that part of our brain to recognize data. So if we think of all the features in the face and we map them to different parameters in our data set, maybe we could learn to recognize certain faces or see patterns or outliers. Okay? Sounds maybe like a nice idea when I explain it theoretically, but when you see an example, it looks a little silly, maybe. So I don't even know what these faces are showing. I'm not sure what an MSA is, but each part of the face is showing a different variable. So the smile shows a level of education. One eye shows a level of information. Another eye shows manufacturing and so on. And there's even the beard and mustache and the eyebrows and the hair. They're all mapped to different things. Now, it might be possible to learn to recognize certain faces and see patterns in data like this. It can lead to some questionable situations, though. It's like these faces show death penalty executions, and the mouth is used to show the age of the convict. So a smiling face shows someone under age 40. Maybe not the most appropriate way to show the data. Okay. So these faces are maybe an interesting idea, but there's many ways we could map the variables to different parts of the face, and that's probably going to bias the way that we see the data. But we don't have to use faces. We could use other things. So any little picture that has lots of little parameters that can be varied and mapped to different variables could be used in this way. So this general idea is called a glyph. So a glyph is any little thing that can be used to show several variables at once. You've probably seen pictures like this. So this is like discrete. It's a discrete vector field on a. It could be used to show wind over a geographic area. So very often little arrows will show the direction of the wind, and the speed of the wind is shown with the length of the arrow. In this particular paper, the authors were also looking for a way to show uncertainty in the direction and the speed of the wind. So they played with different designs for their glyphs. And I think this is the design that they settled on, where the width of the arrow and the extent of the arrowhead would show the uncertainty in direction and speed. So just as a reminder, the data that's being shown here could be stored in a table, like the tables I was showing earlier. So these tables, each column would be one variable, right? Some of the columns are dimensions, some of them are measures. So if we come back to our example with wind here, what would the variables be? Well, there'd be one for latitude, another for longitude, right, to give us a position, a geographic position. And then for each discrete position, we would have the wind speed, the uncertainty in the wind speed, the wind direction, and the uncertainty. So you can imagine 6 columns of data, and then every row is a particular location with some wind through it. So of those 6 columns, which columns would be dimensions in this case? Remember, dimensions are the independent variables. So the other columns are measures, right? The measures are functions of the dimensions. So which 2 columns are the dimensions? Yeah?
The latitude and longitude.
Yes. Because for a given latitude and longitude, we can look up the other 4 quantities, right? The direction, speed, and uncertainties. So with these glyphs, each glyph can show several measures. And in this case, we have 2 dimensions. Here's another example of something that can be seen as a glyph. These are candlestick charts. You may have seen these for financial data, so showing the evolution of a stock over time. These were invented by a Japanese man who traded rice. And he employed, if I remember the story correctly, he employed men who would run between the port where the rice was delivered, and they would run to the market to tell him what the price was or what the delivery was. And so he knew information that other people didn't know. He knew this information sooner than other people, and he could use this to his advantage in setting his own prices. And so he invented these candlesticks where each candlestick shows the price at the opening time of the market, so the start of the day, price at the end of the day, and the minimum and maximum over the course of the day. And the color shows you whether the price went up or down. So there are people who do technical analysis of stocks. I don't know really how reliable it is, but it's a way of summarizing data over several days, right? So we have time here. This is a dimension. And as a function of this dimension, we have 4 measures. There's the price at open, at close, and the high and the low price. So these are another example of glyphs. Here's another example. So every circle here is a country. The color shows the region of the world. The diameter shows the population. And here we've got income measured as GDP per person. This is health measured as life expectancy. And there are animated versions of this chart. So maybe you've seen Hans Rosling on TED. He's given several TED Talks where he shows these animated charts showing the changing location of countries in this type of scatter plot. So glyphs are one way to show several variables at once. There's another technique which I'd like to show by way of Tableau. So Tableau, if you work with data, Tableau is a really useful tool to at least try out. And Tableau can read in a CSV file or Excel spreadsheet, or it can connect to a database. It sucks in the data, and then it has heuristics in its software to figure out which variables are probably dimensions and which ones are probably measures. So we'll list all the columns in the data set in these 2 places. And usually, it does a good job of classifying these variables. But sometimes it makes a mistake. So if it makes a mistake, you can simply drag and drop between these 2 panels to correct it. And what you see here initially is blank. But what you can do as a user is you pick up the variables you're interested in, and you drag and drop them. You can drag and drop them up here or here, and Tableau will generate a bunch of charts for you to show you the data. And it usually does a pretty good job of choosing appropriate charts. So it can generate line charts like we see here, bar charts, stacked bar charts, it has a feature called Show Me, and there's a paper, I think it's an InfoVis paper that talks about this feature. So if you are interested in this data but you want to see it in a different way, you can click on Show Me in the menu, and it shows you alternative ways of seeing the same data. It can show data overlaid on a geographic map. So let's look at one example of a view it can generate in a little more detail. So in this case, the user has drag and dropped 4 variables into these locations. And maybe you see here it says columns, and here it says rows. So right beside columns, the user has dropped region and then weekday. So if we look at the columns, there's 3 main columns, central, east, and west. Those are the 3 regions, right? And within each column, it's subdivided into the days of the week. So that's weekday. Now, right beside rows, the user has dropped market segment first. So those are these 3 market segments, home office, corporate, and consumer. And then the user dropped sum of sales total. That's the axis that we see here. So there's this sort of recursive subdivision along the X and Y axes, which happens as a result of the user dropping these things in. OK, so if I show you a sketch of what that looks like, in general, if we drop in the variables A and X and B and Y, we get this type of arrangement. And so this is another way of showing several variables at once. We're showing 4 variables, even though we only have 1 horizontal direction and 1 vertical direction. And we could continue, in theory, we could continue to subdivide space in this way. So maybe we can call this dimensional stacking. That's one of the terms used in the literature. Another example, here the user has dropped different variables, and we end up with a bunch of scatter plots. So at no point does the user have to explicitly say, I want scatter plots or bar charts, right? Tableau does a pretty good job of choosing that for us. How does it know what to choose as a chart? Well, maybe you notice the different colors here. The blue colored variables are actually dimensions, and the green ones are measures. So in this case, the 2 innermost variables are measures, right? So we've got measure versus measure. Scatter plot is usually a good choice for that. In this case, the 2 innermost variables are a dimension and a measure. So the sales are a function of weekday. And that's why, in this case, a line chart was a good thing to choose. So Tableau makes use of the distinction between dimensions and measures. It also makes use of some other principles to choose the type of chart it shows us. So one of the other things it uses is this hierarchy of visual channels, or hierarchy of graphical variables. And this is a hierarchy that's been established in part through studies of psychophysics, so perceptual studies. And what's been found is that position is the best way of showing quantitative data. So if I were to show you a chart with 2 different positions and I asked you to estimate the quantitative difference between those positions, there'd be some error on average in your estimate, but the error that you exhibit on average is less than if I use some other method of showing the same quantities. So for example, if I showed you the quantities with different colors, the tendency is that there'd be more error in your answers. Okay, so just take a moment to notice in first position here we have position, this channel called position. That's number 1. Number 2 is length. And then we have angle. So I'll show a few examples of these. What do I mean by position exactly? In a bar chart where I have 2 bars that have the same origin, they both start at the same 0 value, right? The positions of the tops of the bars are what we want to compare when we're evaluating quantities, when we're trying to estimate visually how much bigger is this compared to that. Same type of thing in a grouped bar chart. If you're comparing the blue and the red bars, you're making use of this visual channel that we call position. Here, this situation, these are stacked segments in a bar chart, stacked bar chart. So if I asked you to estimate the difference in length between that and that, it's a little bit more difficult as a task, right? Because they don't have the same origin. Maybe you have to mentally imagine sliding one beside the other, and so that introduces a little bit more error. So we call this the length visual channel, and it doesn't function quite as well as using position, okay? So this is the distinction between position and length in the hierarchy. So if I back up again, we've got position, that's the best variable you can possibly use. Length is in second place. Then we get to angle. So charts that make use of angles would be like pie charts, right? And so I'll show you an example of that. As we make our way down the hierarchy, it gets more and more difficult to estimate the quantitative difference between these graphical variables. So estimating the difference in areas, that's more difficult, especially if the shapes are irregular, like skinny rectangles. So density, this is something that we might instead want to call value, right, in HSV color space. Hue, it's really difficult to estimate quantitative differences between hue. So I mentioned studies that have established this hierarchy. There's some old work by, I think it's Cleveland and McGill, yeah. And then there's more recent work that was done using the Mechanical Turk. So have you heard of Mechanical Turk? It's this Amazon service that allows you to, you can do user studies in some cases with hundreds of participants. So you write code and then Amazon will distribute it to people around the world and they can answer questions. And so studies have confirmed the original work by Cleveland and McGill that there is this hierarchy of visual channels or graphical variables. So Tableau, that software I showed you earlier, it makes use of the distinction between dimensions and measures. It makes use of that hierarchy I just showed you, and it also makes use of the distinction between quantitative variables, ordinal, and categorical variables. So what are these things? So a quantitative variable would be like a real number, or a price, or a temperature. It's a quantity where you can do ratio comparisons. You can say this quantity is 3 times bigger than this other one. Okay. An ordinal variable, you cannot do ratio comparisons like that. So an example would be like your level of education. Okay, do you have a high school diploma? Do you have a bachelor's degree, a master's degree, and so on? We can take those different levels of education. There's a natural way to order them, but we can't say that a master's degree is 2.5 times bigger than a bachelor's degree. Okay, it doesn't really make sense to make those comparisons. And then a categorical variable is one where there's no natural ordering to the different levels. So like food groups or countries of the world, you could arrange countries alphabetically, but that's quite arbitrary, right? And if you translate from one language to another, then the ordering changes. So depending on the type of variable you have, there's different charts that make sense. And actually, the hierarchy I showed you earlier, the hierarchy I showed you was only correct for quantitative variables, so things that are sort of like real numbers, right? And remember, I said that color hue, like colors of a rainbow, that's a pretty bad way to encode quantitative variables because it's hard to estimate the quantitative difference between color hues. Well, it turns out that the hierarchy changes if we have an ordinal variable, and it changes again if we have a categorical or nominal variable. And it turns out that for categorical variables, color hue is actually not bad, right? Imagine the food groups. Maybe there's 4 or 5 different food groups. You could give each one a different color of the rainbow, and that works fine. It's quite reasonable as a way to encode color group, the food group. Okay, so Tableau has heuristics that tell it based on the type of variables you have, certain charts become the default choice, and that's part of the intelligence inside the software. And so we as designers can make use of these same rules, or at least use these rules to inform our choices when we're deciding how to present information. So one of the rules is if you have a quantity that's a function of a categorical variable, use a bar chart. Okay, so an example would be price of car versus type of car, or the model of car. If you have something that's a function of a quantity or a function of time, use a line chart. Okay, so maybe keep those in mind. Here's a few examples from an online quiz to illustrate some of the stuff I've shown you. So this is a quiz at perceptualedge.com. It's a series of multiple choice questions where I think it's all 2 choices. So there's 2 options, and you have to say which one is better. So in this case, the question is, which chart is better at showing us the difference between mid-cap US stocks and small-cap US stocks? So we're talking about the blue and orange. So the blue and orange slices here, can you tell which one's bigger? Maybe it's kind of difficult, right? Whereas over here, mid-cap, small-cap US stocks, the 2 bars are here. It's quite easy to see which one's longer, right? So over here, which visual channel are we using? Which graphical variable? Do you remember the hierarchy? In the first place, it was position, yeah. Because these bars start at the same 0. So we're in first place in the hierarchy. Second place was length, and third place was angle. So that's what's being used over here. So this is sort of a demonstration that the hierarchy does work. One of the rules I showed you was if you have a quantity that's a function of time, you should use a line chart. And I wondered, when I first read that rule, I wondered if it really made sense. So here you have the same data shown two different ways, as a bar chart, as a line chart. And maybe I have a very poor aesthetic sense, but when I first saw these, I thought, there's no difference. Why would we prefer one over the other? But usually when I ask students, there's some who can think of a reason why we should prefer this one. So can anyone think of a reason? It's more clear to see the trend as it changes. Yeah. Yes?
It's using position, but the first one is actually using length because the bar.
Okay, so it's good that you have the instinct to analyze it with respect to the hierarchy of visual channels. But actually, in both cases, we're using position because all these bars have the same starting point. They all start at 0. And here, the height of each of the points is with respect to the same 0. But it's an excellent reflex to develop to ask yourself, is this chart really well designed? Which visual channel is it using? Yeah.
Just because when I think time is linear, so it's easy to see the continuous pattern over time. So
Okay.
That's why it's easy to. It's like linking all the positions together.
Okay. So I think I gave the wrong answer to this quiz just to see what the quiz would say. And I think the explanation I gave was something like what you just said. Something about this makes it clear that we're looking at two sequences. We could explain it in terms of Gestalt theory, that perceptually we see this more as two things, whereas this we see as a bunch of things. But I wasn't convinced by that. It sounded really fuzzy to me. And so you mentioned trends and changes.
Can we say that that chart, the bar chart, includes information that you don't need? Because the only thing that you really need is the top point.
Yeah.
The rest of it, that whole box there with the colors and the width of the bar and everything, are the information that you don't really need. So we need to pay attention to things that we don't really need.
Yeah, that's true. And that's been argued by Tufte. Edward Tufte wrote a series of books, and he talks about the data to ink ratio. And I think in one of his books, he actually proposes redesigning bar charts so we just see the tops of the bars. And so I think there's some validity to that point of view, but it can be taken too far, I think, also. But you're right. The width and all the ink inside the bars is sort of redundant. Anyway, somehow I started wondering about slope. I can't remember if I read somewhere that it was easier to see changes in slope with a line chart. So I tried this little experiment. I generated a sequence of numbers, show the same numbers with bars and with line segments. And so I could ask you, from this bar to that bar and this bar to that bar, can you see a change in slope? Maybe you can, but it's not very easy to see. Whereas over here, maybe you do see the change in slope more easily, right? So just from that point of view, that could be an argument for using a line chart for this type of data. This is actually an example from one of Tufte's books. So he found this in probably some newspaper or magazine. It's to show the effect of inflation. Tufte really likes to criticize people, so he takes examples of things that you shouldn't do. And so you have a dollar back in 1958. It's worth 100 pennies, 1958 pennies. But if you compare it to a dollar of 1978, that's only worth 44 pennies from 1958 because of the effect of inflation, right? And so in terms of the hierarchy of visual channels or graphical variables, what's going on here seems to be that the area shows us the value of the dollar. And that's not so good because this, it's more difficult to compare areas than it would be to compare positions. So we could show the same data with a line chart or a bar chart even, and that would make it easier to see the real differences. It would also be kind of boring though. So maybe we want to entertain the reader. So in the context of journalism, if you want to entertain the reader, maybe this type of approach it can be defended. Actually, what's really going on here is it's not the area of the dollar bill that shows the value. It's the height and the width simultaneously which shows the value of the dollar. And that's why this dollar looks like it's about a quarter of the size of this one, even though it should be 44% of that one. So that's really bad. It's very misleading to the reader, right? To be varying the length and the width simultaneously, because that means we have to take the area and square it to get the real, or something like that with it. It's very confusing. Other examples, so here we have the same data. These are meats, different countries. I don't know if it's sales or consumption or what, but you can show the data with stacked bar charts, parallel bar charts, grouped bar charts in 3D, and then we can compare these different options and ask which one is better for comparing two meats from the same country, or the same meat for two different countries. And so for those types of questions, in this chart, we are always using position to compare two meats for the same country or one meat for two different countries, right? Because all the bars start at the same place. On the other hand, over here, if I wanted to compare pork between two countries, like that segment versus this segment, it's not a position comparison, it's a length comparison, right? So I'm in second place in the hierarchy, it's not quite as easy. If I'm interested in the total for each country, obviously this makes it a lot easier to see that, right? Because the total height of each bar is the total for the country. And this type of chart, if we're comparing bars like this within the same row, we're talking about a position comparison, but within the same column, it's a length comparison, right? And in 3D, 3D has lots of problems with it, like there are no position comparisons because of this perspective effect. Sometimes there's occlusion problems, so I can show you really bad examples of 3D bar charts where some of the bars are completely hidden. Yep.
Just a quick question. Are
Yeah.
there any circumstances where 3D charts would be helpful? Because I can't remember.
I don't know. Yeah, so there is a study just a few years ago by Yvonne Jansen, and her co-authors, and they were interested in bar charts of different types. So bar chart shown in 2D on a screen versus in 3D on a screen with stereo cues versus a 3D printout of the bar chart so that you could hold in your hand. And the surprising thing they found in the study was that 3D printout was better than 3D virtual, because the user could hold the printout in their hand and they could touch it, and they could use their fingers as landmarks or bookmarks to help them answer questions about the data. But sadly, the 2D view of the data was better than the 3D ones. Even though in 2D you had to interact, you had to select a slice with your mouse and see the data. It was just, it was better. So maybe there are certain cases where 3D is better, but it's not obvious given the studies that have been done. Just a quick example of color. So I think maybe in engineering and maybe in the hard sciences, we often see these rainbow color maps. And people in InfoVis love to hate on these rainbow color maps because people have written articles about why you shouldn't use them. It's difficult to estimate the quantitative difference between colors. And so this is just one example showing, I think it's elevation and depth around Florida. And so because of the rainbow being used here, there are these artifacts. It looks like there's some boundary here, but it's not in the data. It's just an artifact of the color map that's been used. So a better color map to use for this type of data would be something where you only change one component of the color above 0 and below 0. And at 0, you can introduce a discontinuity in the color map so that it makes the coastline clear, right? Because that's a physical feature you want to maybe have visible. So here it looks like it's just the value of the color that's changing from blue to black. And here, again, it's the value changing from green to white. And here's another article about why. I mean, maybe you know that there's this famous article by Dijkstra from, I think it's the 60s, where the title of the article is something like "Go-to statement considered harmful." Maybe you're too young to. Some of us have seen that before. So here the title is a play on that title. A rainbow color map still considered harmful. Okay, so I showed you some things that were partly motivated by the question, how can we show several variables at once? So I showed you glyphs, I showed you dimensional stacking. That's the approach in Tableau where we recursively subdivide space. What are some other ways to show several variables at once? To introduce them, I'll consider another data set. Let's say we have a bunch of students. Each student is taking the same 4 courses. So we have, Sam is one of the students. They have these marks. And so you could imagine a table with 4 columns, the 4 courses that are being taken, and every row is a student, or every student is a tuple. That's another way to think of this. So one way to show this data is with something called parallel coordinates, which were invented by Inselberg. So every course, every variable becomes an axis, and every student or tuple becomes a polygonal line that intersects these axes at the appropriate location. So, maybe this is Sam, I've drawn in black. This is Tony, another student who's not doing so well in physics and math, but doing better in the other courses. And so we could have a whole bunch of students shown as polygonal lines here. Another approach to show the same data is to take our 4 courses and then to form all the different pairs of courses that are possible. So here I have math versus physics, French literature versus physics. What else? Here's math versus history. Okay, so these scatter plots have been arranged so that every possible pairing of courses is there. And then each student will become a single point in each scatter plot. So the black points here might be Sam, and then the red points are Tony, right? So, and then you could add a whole bunch of students, and you'd end up with all these different scatter plots. So here's another example with 5 students. One of them is in red, one's in blue. There's another 3 students in gray. So on the right, you have parallel coordinates. On the left, you have, this is a full crossing of the 4 courses, right? So this thing is called a scatter plot matrix. And one way to create this, to generate it, is you take your 4 courses and you cross them with themselves, and then obviously you have all pairs. But actually, this matrix will be redundant. It's a symmetric matrix because, for example, here I have dance versus math, and over here I have math versus dance. It's the same information. So there's a diagonal here, math versus math, physics versus physics, and so on. The diagonal is not very interesting because the scatter plots on the diagonal, all the students end up on a line of slope 1. So that's not very interesting to show. And then the upper triangular half is just a reflection of the lower triangular half. So what we often do with scatterplot matrices is we remove the diagonal on the upper half. We only show the lower diagonal half, triangular half, sorry. So if we had lots of data, you could start to see patterns. You might see correlations, right? Someone who's good at math might tend to be good at physics. So we might see a correlation here. You might see outliers. You might see different trends in each of these scatter plots. And it's a way of seeing an overview of many variables at once. OK, so if we take a step back and look at everything I've shown you, on the left we have small data sets with a few solutions for each of them. These are not the only possible solutions, not the only possible charts, but they usually work pretty well. And on the right, you have maybe the more interesting case, the more challenging case where you have several variables at once. So dimensional stacking, there's a limit to how far you can subdivide space, right? You'll end up with either charts that are microscopic or you'll need to scroll forever to see everything. So maybe we could allow ourselves to have, at most something like 6 dimensions here. So 3 vertically, 3 horizontally. It really depends how many levels you have within each dimension. But if you add too many, you very quickly end up with an explosion in the number of charts here. So other techniques I showed you, glyphs, parallel coordinates, scatterplot matrix. They're good at showing many measures, but they don't really help us show lots of dimensions. And maybe I haven't shown you why. So I'll show you in a few slides what happens if you try to show many dimensions with these techniques. But the point I want to make with these examples here is we don't have a solution for the case of having many dimensions. We don't really have something that scales up to many dimensions. So there seems to be an opportunity here to come up with a new solution for that. And so that's one of the projects I worked on with a student at ETS. So to explain this a little more, consider another example data set where we have this table of data. We've got some factories that manufacture nuts and bolts. And we have 3 dimensions, so their factories are located in 3 different regions. We have data for the 12 months of the year, so the months are numbered 0 through 11. We've got our 2 products, nuts and bolts, 0 and 1. And for each of these, we have sales and cost numbers, right? So we'd like a way to visualize all this data. 6 variables, 3 dimensions, 3 measures. We could try to use a scatterplot matrix. So I've just formed all the possible pairs of variables here. And we notice something strange here. What's going on here? I've got things like month versus region. Well, month and region are both dimensions, right? I've got 12 months, 3 regions, what I end up with is just a grid, a regular grid of points. That doesn't really help me understand the data. It just tells me, how many regions and how many months I have. So in these 3 plots, we have these strange grids of points that it seems like something's not working. There's something similar that happens with parallel coordinates. If we just take the data and plot it in parallel coordinate form, on the right I have my 3 measures, and maybe we can start to see some clusters and outliers. But over here I have my 3 dimensions, and all this is showing us is that every possible combination of these 3 dimensions is present in the data, and maybe that's not the most informative thing to show us. What if we try using dimensional stacking, like Tableau might use? I have 6 variables, remember? So 6 variables, if you do dimensional stacking with all 6, you get something very big. So you have to scroll a long time, or you have to end up showing the charts as being very small. If I just take 4 of the 6 variables and show those, I can get arrangements like this. So here I have like product, and then inside that I have sales. Here I have my region, and inside that I have my 12 months. Right, so this is just 4 variables. If I add another 2 to show the whole data set, there's this combinatorial explosion that happens. Over here, there's another 4 variables that are being shown at once. And over here, again, just 4 variables being shown. So just nesting product inside month, that already takes a lot of space, right? So dimensional stacking doesn't scale well to a large number of variables. What about glyphs? Well, recall these 3 examples I showed you. Glyphs can show many measures, but they cannot show many dimensions. In this example, we had the different countries arranged within a scatter plot. So the 2 axes, the 2 outer axes here were measures, and every glyph just adds additional measures. It shows us the region of the world, the population. So we're not showing any dimensions here. In this one, we had a single dimension shown along in this axis, and in this example, we had 2 dimensions. But how do you go beyond 2? You could add a 3rd dimension, but then you'd have like this volume filled with glyphs. You'd have a lot of occlusion. It'd be hard to see anything, right? Maybe you could add a 4th dimension if you add animation. So over time, you can show an evolving volume of glyphs, but it would be really difficult to understand that. And I don't see any way to go beyond 4 dimensions with glyphs. So they just don't seem very amenable to scaling to many dimensions. Okay, so what we ended up doing, my student and myself and our collaborator, there's 3 of us, we took the idea of a scatterplot matrix and we said to ourselves, inside each cell of the matrix, we don't have to have a scatterplot. We could put something different. So we form the matrix, and then inside each cell, depending on the combination of variables we have, we choose an appropriate chart. So if we have 2 dimensions, we stick a heat map there. If we have a measure versus a dimension, we put a bar chart. And if we have measure versus measure, we put a scatter plot there. So this thing we called a GPLOM, just to use an acronym. And so my student implemented this, and he got it to visualize, if I remember correctly, hundreds of millions of flight delays. So he somehow got a data set of delays of flights. And he, with this interface he made, he could visualize the reason for different delays broken down according to different dimensions. And there were ways that the user could select a category within a dimension, move the cursor over other categories and see parts of bars highlighting to show the links between the data. You could also dive into one particular chart and see details about that. So he ran an experiment that compared this to Tableau. And so with Tableau, what ends up happening is the user doesn't see anything initially. With Tableau, the user has to drag and drop variables to generate charts to answer questions, right? Whereas with our interface, the user could see an overview immediately, and then they could dig into a single chart to get more information. And what we found is that this interface it allowed the user to answer certain questions faster than Tableau. So we wrote up a paper about this, and we submitted it to InfoVis. And then the day that we were supposed to submit it, I think it was March 31st probably, my student emailed me, and he said, Mike, you should really look at this paper by someone else that I found. It looks like an interesting paper. Maybe we should cite it. So I followed the link, and I found the home page, And I looked through the list of publications, and I found there was a publication that it was a journal article that had come out 4 days prior, and it had a title that was very similar to our title. So then I downloaded and looked at it. I thought, wow, these researchers came up with a very similar idea. And it turned out that their idea was several years old, and it had only been recently that they got around to publishing it. So I had to quickly rewrite the introduction to our paper. Instead of saying that we have a new technique, I had to explain how it was an improvement on this other technique from 4 days ago. And we were really lucky we got it in. Our paper was still accepted. So actually, in my career, it's happened 7 different times that I've seen 2 teams come up with very similar ideas, or my own team and some other team has come up with very similar ideas right around the same time. And I've had other researchers tell me that it's happened to them too. So I guess it's just something inevitable. Okay, so maybe this is a little complicated for someone to understand. So maybe the most useful idea within all this is this sub-matrix. It's the one that crosses measures with dimensions. Maybe this could be an interesting way to show an overview of a database, right? So if I take my nuts and bolts database, I can show just the measures crossed with the dimensions, and we get a matrix of bar charts. And if you like, there's an implementation of this in D3. If anyone here uses D3, there's an implementation of it that shows you how to do this. So there's my summary slide that's been updated. And let's see, how much time do we have left? Not much time. Not much time. Okay. So I'll skip over some stuff. I will mention, if you're interested in this type of thing, this topic of InfoVis, and you're looking for a good book, the best book I know of is by Tamara Munzer, who's a professor at UBC. So her book is maybe not, like if you're a designer, if you're very hands-on and practical, this might not be a book that you like. Maybe someone who's very hands-on would prefer a book that has lots of examples of things to do and not do. And I think there are several books that are like that. This one is maybe a little more theoretical, but I really like the way it's written. I find it very complete and rigorous and very clear. So if you're interested in the theory of visual channels and how to go through the process of designing the visualization and evaluate it, this is the best book I know of. There's also several surveys of literature that are available. So this is just one. It's called treeviz.net. And so it was published as a paper, but there's also a website you can go to. This particular one is a survey of different visualizations of trees. And so you can see all these thumbnails. There's more than 300 of them, thumbnails of different visualizations of trees. For each one, you can click and see the paper, and you can filter the thumbnails by different criteria. And I think this particular website and this survey started a trend among researchers, because subsequently there are many other surveys that came out that had companion websites. And so if you click on the menu here, you can see all these other surveys that were made by other researchers on different topics. So biological viz, we did one on financial viz. There's stuff here on set visualization, space-time cubes, okay? And these are not, this is not a complete list. There's other surveys within InfoVis on other topics as well. But this is a good starting point. So here's our Finance Viz website. Now, I see I'm out of time, so I will not show most of the other stuff I'd planned to show. Maybe I'll just show one example of some research. So this is some stuff I did during my PhD. I was interested in visualizing volumetric data. So this is a medical image of someone's head. And we were interested in trying out different ways of allowing the user to open up the head and look at the layers of tissue inside it. So I have like a video I can show you of that. Now it's pretty low resolution because I'm not a computer graphics person. There are ways with modern hardware that you could do a much better rendering, a much higher res rendering than this. But this was done back in 2002, 2003. And you can see the user there is opening up a radial menu, and they're performing flicks, rapid left and right flicks with their mouse to cause different layers of the data to either be deformed or to close back. There are also various yellow widgets that the user can grab with their mouse to drag on different parts of the data. I think we may have skipped over some part of it there. But here, so the user here has just opened up certain parts of the volume. They can adjust the axes of rotation. So again, that radial menu is being used to flick left and right to close or open different parts of the data. And then next we should see another tool that the user can use. Yeah, so this one's called the peeler. So what happens here is we have a sequence of arrows. Each arrow is associated with a different layer of the data, of the volume. And the user can drag on the arrows to sort of peel back the data. So we had an earlier version of this software, and it didn't have all these interactive widgets. What would happen is the user would hit a key, and then it would snap into a deformed state where the head is opened up. And we found that that was very disorienting. So initially, you'd see the head as it normally would be. You could press a key, and you could deform it in different ways. But the deformation was instantaneous, right? It would suddenly snap with the head split open in some strange way. It was very hard to tell if it was operating correctly or not, because there might have been bugs in our code, and we couldn't really tell what was going on. But in this version of the software, because the user is gradually peeling things open, they see a continuous change in the representation of the data. And you can see, you can understand the metaphor of what's going on physically. Okay, here I'm peeling, here I'm hinging something open. And so this is maybe an example of a more general idea that whenever you show a change in a view, you should, if it's possible, you should animate the change. So there's some work that's been done to show animated changes in different statistical plots, right, between scatter plots and bar charts. There are different ways you can animate the data to cause the bars to shrink down into points, or have the points move around, or have the bars rearrange. And this really helps the user to understand the changes in the views. So this is something that's not necessarily easy to program, but if you can do it, it really helps people understand different ways of looking at data. So I have more stuff I could show, but I should probably stop now for questions. Any questions on stuff I've shown? Or yep?
Talking about this, I'm just curious, when doing the animation to show the change, how would they actually do that? So how would you go from the point to the bar chart?
So I have a video of this project. So this is not my work, by the way. This is Jeff Hare and I think it's George Robertson. So that was bar chart to pie chart we just saw. Back to bar chart. Now scatter plot. Now it looks like the data is being sorted in different ways. Decomposing into a stacked bar chart to show segments of the data. And then we can transition to a group bar chart. Here's a change in perspective to a 3D bar chart. Here we're adding more data. I say we, but I wasn't involved in the work. I think this is animation over time, changes in scale. And then this is interesting. You see all the bars moving at the same time here, right? Now watch closely. There's going to be another condition. Here they don't move at the same time. So that thing we saw at the very end, the motion started at one end, and then at the end the last few bars reposition themselves. So that's something that they call staged animation, where the bars do not move all at the same time. And it's to help avoid occlusion. And so they have experimental evidence that staging helps people understand the animation better.
So considering that the animating from one type of presentation to another is not necessarily a single solution problem, is there any study on what type of animation would work better?
Yeah, there's been subsequent papers. So I could point you to some papers if you're interested. I think there's still a lot of open questions around this though, because there's many ways that you could animate things.
Yeah.
So another approach is if you want to have different views of the same data, instead of animating between those views, what you can do is show the views side by side. And then you can have things like if the user puts their cursor over here on some data elements, you can highlight the corresponding data elements in the other view at the same time. So that's sometimes called coordinated views, or brushing and linking. So here's an example. We have, there's actually 4 different views here. There's 2 big ones and there's 2 small ones at the top. And the user has selected 2 subsets in red and yellow. And so there's red and yellow highlighting in the other views as well. And that's another way to help people understand the linkages between different views.
Any other questions? Okay. Thank you so much for
Okay.
the presentation.
Thanks for attending.